Last time, welcome back to COMP526 for this time. Efficient algorithms. We have one more unit. That's kind of my bonus unit, full of some neat ideas, but also a bit on the side. So I took it out of the exam material, but I think it very nicely fits into the theme of this lecture. Maybe just the last bits are a bit too advanced, so I wasn't courageous enough to demand that from you. But I still think you can enjoy it very much. Let's see. It's about the range minimum problem, and I'll introduce that, what that means, and you'll immediately recognize it after a few slides as something familiar, but in disguise. I mean, I do have learning outcomes, even though they're not assessed. So, well, I still have the goal that you understand what this problem is and its connection to longest common extensions. Okay, I gave that away now. I think everyone can understand these simple solutions, which are not unreasonable to use as well, especially the sparse tables. Then a bit more interesting is a connection to something called Cartesian trees. I'll get to that. And then the advanced bit is the exhaustive tabulation technique that allows us to get to the final performance. We'll come to that. It's a relatively short unit. I want to introduce this problem a little bit and then the successively more advanced solutions. Let's first see what this problem is about. Abbreviated as RMQ, the range minimum query problem is given an array of numbers, or could be other objects. It's entirely comparison based. Say an array of numbers. And the goal is, the game is as follows. I give you this array up front, and you can have a look at it. You can take notes. You can build a data structure. And then later on, I will ask you for range minimum queries, which is given a range from I to j, where in that range is the smallest value. So here's an example array and an example range. And then you can find, well, the smallest value in that range is the 2, and it occurs several times. So the definition of the range min query problem is to find the leftmost minimum. That's somewhat arbitrary, but you have to break ties somehow. And also we'll return the position where you find the minimum instead of the actual value. Now that's not a big restriction. You can just look in the array what's there. But this will come back later. Will come in handy in a later section. It just turns out to be this is more convenient. Okay. So relatively simple definition. Now, I mean, I haven't told you why this is at all useful. This looks like a nice exercise problem, an etude in music. You just check if you can solve this, but it has very, very good motivation. But before we get to that, let's make sure that the definition is clear. So here's no trick question, just checking if you're getting all the bits right. An example array and a query. This is not about your ability to take the memory. So if we're given this range from I to j, right, both endpoints are inclusive in this case. It's maybe a bit inconsistent to how we handled ranges otherwise, but I chose it this way in this module. I know it's early in the morning. I feel for you. I have my coffee. Someone sent a sleepy smiley. Oh, no, then you can see the array. We had 23 votes for the attendance code, so maybe we can, it's 9 people who voted. We will give you a few more seconds. But I don't want to bore the ones in the room. Shall we say 15 is the magic number? That would be 3 more. On the other hand, it looks like all of you are done, and that's mostly... Okay, we got one more. I don't feel very patient. Let me show the results. So again, in this image, you don't see it so well. 4 people voted for 1, and then all the other options. Okay, 2 people voted for the 4, 6. For some reason, it doesn't show the commas. There's commas in the actual answer. Weird. Okay, someone decided for these word diagrams, we don't want commas. But the emoji survived. That's the important bit. All right, let's briefly go through this. Nothing complicated. So we take our range. I said both endpoints are inclusive, so we have this range. And now we find the smallest value in that range seems to be number 4. It occurs 2 times, but the definition said pick the leftmost. So this is our minimum. And then the second nitpick was what you should return is not number 4, but the position 1. So that's the answer. No. Okay, I kind of I trained myself to write the ones like this so that they're more distinct from other things, but then people often mistake it for a 7 or something. So I have to be very careful to write it clearly. Good. So we understand what the definition's like. That's good. A few observations. The way it's defined, it just asks for minima. And because it returns just the position, the queries actually know nothing about the values in the array. And there's this notion you can talk about 2 arrays being essentially the same for all arrangement queries. The answer of the arrangement query is just the position. So if you have an array and you add a constant to all the numbers, for example, it doesn't change any of the minima. So many arrays will turn out equivalent with respect to these arrangement queries. All right. Now for this data structure problem, there's, unlike before maybe, there's several things that are important or interesting to look at. One parameter is the pre-processing time. That's the time you spend when I give you the array up front before we can start the game of actually answering queries. And I'll call that P of n, like pre-processing. Notice that the way we define the problem, the space usage of your data structure can also be at most P of n, because you have to create that data structure from scratch. You have to write it. And so you can't even touch more memory than P of n if you spend so much time. So in a way, this is 2 parameters. It's the pre-processing time and the space for the data structure. But we'll see that this is always bounded. So by minimizing the pre-processing time, we, through the back door, also make sure we don't use much more space. And the second parameter is the query time. That's the time for answering 1 query. OK. To have a short notation, I use these angle brackets. So the important bit is just P is before Q in the alphabet, and pre-processing comes before query. So the first parameter is how much time do you spend when you're given the array first, and then the query time is the second thing. OK, let's do a guessing game. I haven't told you anything else, and so you can't know. But I'd like to ask you to just guess. What do you think might be possible? What do you think is a reasonable pre-processing time and query time? Just from your gut instinct. and then you can later compare to the solutions I'll show you. Now, okay. Good. So what you're supposed to send is something like a pair of two functions in n. So it could be, again, I don't want to anchor you on anything specific. Let me put something so ridiculous that you probably won't be anchored to it. You could send angle bracket open 2 to the n, comma 3 to the n, angle bracket close. I hope you won't come up with that exponential time, because that's way too slow. Let's just leave that open. And while you make up your mind, I'll show you the motivation for that ARM-Q problem.